Hi guys, welcome back to part 2 of this Way ANOVA or One Factor ANOVA example that we're doing with the parachute suppliers. So let me scroll down. So in the first video we discussed the problem, what the problem was asking, the setup, the data, and we formulated a hypothesis statement as our first step, right? So this was step 1. Now step 2, so you should always have this as your step 1. For step 2, I would recommend you use this opportunity to gather information. So this will make step 3, for example, which we don't haven't talked about yet, a lot simpler. Okay, so what do I mean? So here I have a bunch of symbols, and this I've discussed in the notes for One Way ANOVA. I have a few symbols. I would like to attach actual values to those symbols. So remember we had the symbol C, which was the number of groups or number of populations that were what we have in our example. Here there are 4 suppliers. Each one of them represents a population for us, so C is 4. Okay, this will be useful when we get to our formulas. N for us, I defined N in a one-way ANOVA to be the total number of observations across all the groups. So in this case we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. And if you just eyeball it, you'll see, you don't have to count them all, you'll see we have 5 from each supplier and 4 suppliers, so N is going to be 20. Okay? N subscript dot. This is my little convention for the number of observations, so the number of measurements we took, right, in a particular group or from a particular group, from a particular population, in this case from a particular supplier. Okay, now you'll notice that this is what's called a balanced design, and it's balanced because each of the groups have the same number of measurements or observations in them, namely 5, right? So count any one of them, all of them should be the same. In this case, this is called a balance. That's why it's called a balanced design. And the examples we're going to do are going to be balanced, and the formulas that are forthcoming, for example, in step 3, are going to be a lot simpler because of this fact that this is a balanced experiment. Okay, so in this case 5, right? So just take any particular group. Once you notice it's balanced, you don't need to you don't need to count them all, right? Because they're all going to be the same. So N dot is 5. Another important thing for us to get out of the way here are some summary statistics. So X bar, but notice when I say X bar now, I'm going to attach a little subscript 1, so I know I'm talking about the mean, sample mean from supplier 1, right? This one and this one, if you recall from step 1, refer to supplier 1. So that's everything to do with supplier 1 when I use a subscript of 1. So I need to get X bar 1, X bar 2, X bar 3, X bar 4. Okay, so how do I get X bar? Well, let me do one of them with you, and then I'll give the rest of the answers, and you can pause and see how I got those results. So X bar 1, for example, well, I have to sum up from 1 to 5 because there's 5 measurements, right? So from 1 to 5, all x1i's. and then divide that by how many observations there are. All that's saying is add up 45 plus 43 plus 14 plus 12 plus 32. I'm getting these numbers from right here, right? And then divide by how many there are, which is 5, which is, it's no surprise that that's the same as this value, right? So once I do that, okay, and once I have kind of punched these numbers into my calculator, I see that the mean tensile strength, the sample mean tensile strength from supplier 1, which is what this symbol is indicating, sample mean as opposed to population mean. We don't know this, right? This is what we want to know, but we have to settle for a sample, okay? Is 29.2. That's what I get from here, okay? By just averaging these guys, all right? And when I actually go through and I do the same thing, which takes a little bit of time, but it's not difficult to do for all of these suppliers. Okay, let me erase this a bit. I get these figures. Okay, so 29.2. For supplier 2, I get 22.4, so you could check these. I get 28.8 for supplier 3 and 28.8, funny enough, for supplier 4. All right. So these are not difficult to do, but they do take a little bit of time, I guess. Okay, so we need to get these out of the way. Okay, let me erase this. What else should we do in step 2? Well, there's still some other information that would be nice to gather before which will make our life a lot easier after this step. So let's get what's called the grand mean. And let me put this here, x with 2 bars on top of it. We say x bar bar, and we call that the grand mean. And what this is, it's the mean of the means. So basically, if you were to treat all this data as if it came from one source, okay, what would be the average, the sample mean? Okay, so basically I'm going to add up all these numbers and divide by 20 because there's 20 numbers. Or another way to do it, and you'll get the same exact result, because there's the same amount of observations in each of the groups, I can take the average of the averages and it will be the grand average. So what do I mean? I could do 29.2 plus 22.4 plus 28.8 plus 28.8 and divide that by 4, only because there are the same number of observations in each of the samples. Okay, and whether you do it this quick and easy way, which I'm doing it, or you do it the long way by averaging all of the values, you will get that the grand mean is 27.3. Okay, so you should also check that, maybe the long way and the quick way I did it here. Okay, now that's not all we need here. We also need something that's even more difficult to deal with, but cumbersome, which is the sample variances. So we need s squared 1, which is the sample variance from group 1, s squared 2, s squared 3, s squared 4. So those are the 4 sample variances. Remember, s squared was the symbol for sample variance, whereas sigma squared was the symbol for population variance. Okay. Also remember that the relationship between the standard deviation and the variance is simply that the standard deviation is the square. Sorry, the variance is the square of the of the standard deviation, and the variance, if you take the square root of it, you get back to the standard deviation. Okay, so you can go between standard deviation and variance quite easily, and you should understand the relationship between those two. All right, so how do we calculate the actual standard deviations here? So let me scroll down a bit and get a little bit of new canvas to work with. So I'm going to just do one of these, and then you can replicate this for the other 4. Okay, so this is quite time-consuming process. So I'm going to do one of them, and I'm going to say to you that you should be able to do this by hand. However, there are also easier ways to do it with Google Sheets or Microsoft Excel, which will make it quick and easy. But both of those would require you to actually put in the data into those softwares. So you keep watching these videos. As long as you're watching all of them, you're going to see that there's a few ways to do all these things, and it's going to make your life a lot easier, as well as give you ways to check things. Okay, so let me show you the formula for variance. So let's do it for, so recall the formula for variance was you go through each of the observations. So since we have 5, I'm doing it for group 1. Okay, from supplier 1. So there's the subscript 1. So because this is 2, this is 3, and this is 4, I need to distinguish them. I take each of the observations from supplier 1, so that's a 1 and then an I subtract the mean, which I calculated here, right? And then I square that. And then after I'm all done, or as I go through it, I divide by n minus 1. In this case, n is n dot, right? So you don't need to memorize this formula. This is basically just applying the variance formula to each of the groups separately. So if I take off this subscript, and I take off the dot here, and I take off the 1, and just leave the I, okay, that's the formula for sample variance. Okay, so let's go through this for the first group. So I do 45, so this equals, maybe I should start a little bit, give myself some space. So 45, that's the first x1 minus the mean, 29.2 squared, plus, that's what this capital sigma is telling me, to add the elements. I go to the next one, 43, that's this number here, minus the mean, that doesn't change, squared, plus the next one, 14 minus 29.2 squared, 12 minus 29.2 squared, and finally we're just going to make it 32 minus 29.2 squared. So I went through each of these observations. So this is only for supplier 1. So notice I used x bar only for supplier 1. Then I divide this whole thing, okay, and I'll leave these individual calculations to you. You're capable of doing this on your own. These should all be positive numbers because you're squaring them, okay? I'm going to divide this by n minus 1. What's n here? 1, 2, 3, 4, 5, minus 1, so that's 4. Okay? And if you go through this whole thing, you'll end up with 243.7. So that is s squared for supplier 1. That's what the 1 is. The s squared is sample variance. The 1 indicates it's sample variance for supplier 1 or for group 1. Okay? Now, if I want the standard deviation, okay, I'm not saying I do, but if I'm asked to calculate the standard deviation for supplier 1, the sample standard deviation, this is the symbol, the subscript just tells me it's for supplier 1, I'll take the square root of the variance. It's as simple as that. Okay, you don't need to go through the whole formula again. If you have one of these, you can get the other one easily, and vice versa. If I have this one, I can get this one. Okay, and what is the square root of 243.7? Well, I pulled up a little Excel spreadsheet and I saw that it's 15.61, so do that with a calculator, or you could use a spreadsheet as your calculator. So 15.61 is the standard deviation. Now what if I knew this and I was asked to get the variance? Well, we're going around the loops. I take 15.61 and I square it and I get back to 243.7. So I think I've made my point clear. The relationship between the standard deviation and the variance is just basically taking the square or square root depending on which direction you're going. Okay, so if you're given one, you can get the other, okay, easily. All right, sometimes I'll give you the standard deviation and I'll ask you, you'll need to know the variances. You don't need to go through this whole process. You just need to square 15.61. Okay, so anyway, so we got this guy, 15.61. Let's go back and write them there. It's getting a little tight here. This is all part of my step 2 gather information stage. Now I need to do the same thing for supplier 2, 3, and 4, exactly how I did here. All right, so I'm gonna just do that using software and save myself some time, but you can go through that process. If you do it for all 4 and you can check your numbers with the ones I'm about to give you, you will be comfortable doing standard deviations and variances rather. Okay, so okay, and if you actually went through and got those standard deviations for supplier 2, you should get 145.3. For supplier 3, you should get 80.7. Supplier 4, you should get 26.2. Okay, so this now will round out our step 2. I know this was a long one, but this will make step 4 a lot easier. So let me erase a lot of this extra stuff here so we can get a nice kind of clear picture of what we did in this step. Okay, that was 27.3. I'm going to write that there. And so we have 27.3 was the grand mean, double bar, right? So this whole step right here that we did would be our step 2. If we scroll back up, okay, step 1 was to write the hypothesis, understand the problem. Step 2, gather information, and here are the symbols that I use. And these symbols are going to become useful because in the next step, these guys are going to work into the formulas that we've discussed. Okay, so watch part 3 to work on step 3. Hi, welcome back to step 3 of our one-way, one-factor ANOVA problem on parachutes fabric. Okay, parachute fabric. Okay, step 1, hypothesis test. Step 2, gather information. Step 3, here are the actual, we're going to get the actual value for our test statistic, which is going to take us home. So we're going to get S squared pooled. That's a subscript pooled, right? Remember, this pools the variances that we discussed here, that we calculated here. So pools them into one number. S squared x bar, that's a subscript x bar. This is the variance of these x bars. Okay. And finally, once I have those, I can calculate my F statistic, or just F. This is my test statistic. That's what all this is culminating to, is my test statistic, which is an F test statistic. Okay? So let's get the easiest one first. S squared pooled. That's a S squared with a subscript pooled. All this is an average of the S squared. So basically you're going to pool these into one number. So 15.61 plus let's go across 145.3 plus 80.75 plus 26.2. All these came from here. Divided by, well, if I'm averaging them, there's 4 numbers there, so divide by 4. So if we actually go through this and calculate this, we'll get a value of 124. So I did that in an Excel spreadsheet, so I'm using it as a calculator. Okay, so use your calculator or a spreadsheet software like Google Sheets or Microsoft Excel. However you want to calculate these values, it does not matter. 124 for the pooled variance. Next, we're going to get S squared x bar, which can be understood as the variance of the x bars. Well, here are the x bars. We're asking how much do they vary from each other? How much variability is there? Specifically, what's the variance? Okay, so we're going to take each one, subtract it from its mean, which is x bar bar. So we're going to take each one of these, x bar I. We're going to subtract it from x bar bar. We're going to square it to take care of the problem of negative values. Then we're going to divide by c minus 1. There's c of these. There's 4 of them, so minus 1. So that's going to be 4. And we're going to sum them all from I equals 1 to c. So that's the formula we've discussed. So let's see how that actually pans out. So we'll start with x bar 1, 29.2 minus x bar bar, 27.3. I square it. Plus, that's what this E looking thing is, the capital sigma. X bar 2 is 22.4 minus x bar bar, that's still 27.3, that doesn't change, squared, plus x bar 3, 28.8 minus 27.3 squared, plus finally we get to x bar 4, which is also 28.8 minus 27.3 squared. Then this whole thing divided by c minus 1, so that's 3. Okay, and if you go through that, and let me see what I got on my spreadsheet. I get 10.71 if I round to 2 decimal places. So 10, let me write it here, 10.71. Okay, so we got s squared pooled, we got s squared x bar. Now f is very easy to get here. F, which is our test statistic, this is what all this has been culminating to, is n dot, which for me was the symbol for a balanced one factor ANOVA, where meaning all the groups have the same number of observations. So n dot, let me put that in parentheses, times s squared x bar, which we just got, over s squared pooled. We have all these values. N dot was 5, s squared x bar 10.71, s squared pooled 124. These came from right here and right here. Okay, and if you were to actually calculate this, and let me see what I get, I think I got something in the neighborhood of 0.43, yeah, 431807. I don't care if you're not getting this precision. In fact, let me just round it to 2 decimal places to eliminate any extra confusion. Okay, so 0.43. Wow, so that is step 3. this value right here is really what we're going to need to make our final decision, which is going to be in the final part of this video. Step 4, we're going to finally be able to make a decision, meaning reject or fail to reject the null hypothesis that we set up at the very beginning. Okay, so keep watching part 4 to round out this example. Hi guys, welcome back to part 4 of our one factor, one way ANOVA example with the parachute manufacturer. So thus far we've stated the null hypothesis and alternative. We're using a level of significance of 0.05. That's going to come into effect in this step. We gathered information which took us some time to calculate some of these x bars and the x bar and the variances. Step 3 was a little smoother, although it looks more complicated with the formulas. We got s squared pooled, s squared x bar, and we were able to calculate our test statistic. And our test statistic was 0.43. Now, our final step is going to be to make a decision. And remember, hypothesis tests culminate with a decision, either to reject the null hypothesis or fail to reject the null hypothesis. And some of you may have learned the two decisions are either you reject the null hypothesis or you accept the null hypothesis. So however you've learned, I tend to use fail to reject, but I don't want to get into discussion about which is more correct. Use either. Okay, so here we're going to make a decision on our hypothesis test, which was what all this was about, what step 1 was about. We're going to finally be able to see, to answer the question, is the mean tensile strength the same for all 4 suppliers, or, which is what HO is saying, or is there at least one difference or one inequality among the 4 suppliers? In other words, is there at least one of those suppliers that has a different mean tensile strength than the others? Okay. So we take our F, which we got in the previous step, which was 0.43, okay? And now we need to go to a statistical table. So there's 2 ways to do this. Since we're doing this series is all about doing an ANOVA by hand, we're going to use a statistical table. So the F table requires 3 things from us. 1, our level of significance. 2, a numerator degrees of freedom. So DF stands for degrees of freedom. So we'll call this DF1 or DF numerator. Okay? And a denominator degrees of freedom, sometimes called DF2 or DF denominator. Okay? So we need these 3 things. So for us, these are clear. So maybe I'll switch a color. Okay, for us, alpha was told to us to be 0.05. We're told to test at 5% level of significance. Our numerator degrees of freedom, we know how to calculate this. This is C minus 1. For this example, if you go back to step 2, you see that C was 4. Right? So C minus 1 is going to be simple, 3. And the denominator degrees of freedom, or degrees of freedom 2, is calculated N minus C. So N was, let's go see, this is why that step 2 was so important. N was 20, C is 4, so 20 minus 4, 16. So once I have these 3 pieces of information, I can go to my statistical table, which I'm going to try to superimpose on top of this video capture. Okay, so this is the F table that I typically use in my courses. So you see, first off, that there is a picture at the top right. So I'm not showing you the full thing because I think you won't be able to see it if I don't zoom in like this. So at the very top, you see there is this picture. Okay, And that picture is a generic picture of a F distribution. It's typically a right skewed distribution, okay? And what we're going to get, and important thing here to notice is this whole table is for alpha 0.05, which is exactly what we needed. That was our alpha. If you had a different level of significance, a different alpha, you would have a completely different table, okay? So I'll try to limit it, my examples, to the tables that I supply you, namely this one, okay? So we're in the right place. Next, you'll see that this table is organized into a degrees of freedom numerator going along the columns and a degrees of freedom denominator going along the rows. So basically your job is to match your degrees of freedom numerator, which was also called degrees of freedom 1, which was 3, to your degrees of freedom denominator, which is degrees of freedom 2, which was 16. So I gotta scroll down a bit. Hopefully I won't. Actually, you might be able to see it here. So you see that if I go all the way down until I get to 16, I go all the way right until I get to 3, I get to my F upper critical value, 3.24. Okay? 3.24, you should be able to find that easily on the table. Okay? So that is my FU, no pun intended. The U stands for upper critical value. Okay? FU is different than just plain F. Remember, F was something we calculated with a lot of work from step 2 to step 3. That was 0.43. That was calculated using our data. That's all started from the data that we collected here. Okay? So don't confuse that with what the number that we got from the table, which was 3.24. We just got this from the table. Okay, so keep those two things quite separate in your mind. Our final step is now to compare these two, and let me just write them next to each other. Because we did all this hard work, let's make a nice organized final decision. We see clearly that F is less than FU. And we know that if F is less than FU, we fail to reject the null hypothesis. Okay, that's our conclusion. Okay, remember, if F is greater than FU, we reject the null hypothesis. Okay, but here clearly F is not greater than FU, it's a lot less than FU, so we fail to reject or accept, if you like, HO. Okay, I'm not gonna go into the subtleties of that. All right. Let's just go back and see what HO said. HO said, remember, in words, this is HO. HO says in words that all 4 suppliers have the same mean tensile strength. Okay? So after doing all this work, we see that we don't reject HO. So we conclude there's not enough evidence to conclude that the 4 suppliers have any difference, or let me put it this way, and conclude there is no significant difference among the 4 suppliers with respect to the mean, or their mean tensile strength, because that was our variable, right? That we were. Okay? We can't conclude that there is a difference. All right? So remember, in this example, the factor, or the factor was the supplier. The levels of the factor, there was 4. supplier 1, supplier 2, supplier 3, supplier 4. Those were the levels. So from each level we collected data, and we collected the same amount of data from each. That was the balanced design. That made our lives a lot easier, believe it or not. Take my word for it. The fact that we took 5 observations from each. And our variable was tensile strength. Okay, so we had one factor, hence one Way ANOVA or one factor ANOVA. The factor had 4 levels, so we ended up with 4 groups or 4 populations. We took a sample independently from each of those 4 populations. That was the data that we were looking at up here. Okay, that's gotten all messy now. And then we went through a bunch of steps, namely step 2 and 3, where we calculated a bunch of things, and then we got to a conclusion in step 4 that said we failed to reject the null hypothesis, which was that all 4 suppliers have the same mean tensile strength. And the variable, by the way, is a numerical. That's important. It's a numerical variable. That will always be the case for ANOVAs. All right? Now, if I conclude that there's no significant difference between the mean tensile strengths of the 4 suppliers, in other words, mu1 equals mu2 equals mu3 equals mu4, this is basically my conclusion, then do you think that there's any reason for me to continue this investigation to do perhaps a Tukey-Kramer multiple comparison procedure? No, right? There's no reason to see where the difference comes from specifically, which is what Tukey-Kramer purports to do, if, in fact, we've learned that there is no difference between the groups. So, no reason to continue to do a Tukey-Kramer here. You would only continue to do a Tukey-Kramer if, say, your F statistic was, let me just put a 1 there, so this became 10.43. So this inequality would go this way. We would then in turn reject HO, and we would conclude that there is, take out the null, a significant difference among the 4 suppliers with respect to mean tensile strength. And then in that case, we rejected HO. So our conclusion, let's go back. We rejected this. So I could put a line through this. This is hypothetical. That's not what happened. Well, let's say that's what happened. I would conclude that there's strong evidence that there's at least one inequality among the 4 suppliers with respect to mean tensile strength. So now I'm concluding, I would conclude ALOI, which means that at least one of these suppliers is different than the others, or all of them are different, or some pairs are different than other pairs, or triplets are different than some other one, and so on. There's a lot of possibilities. In order to explore those possibilities and find out specifically where those differences may be coming from, in other words, to find out whether they're all different than each other, whether it's just one's different than the others, One Way or One Factor ANOVA won't do that for you. It will do this broad test. But in order to get down to the details, if you reject HO, you would continue to do a Tukey-Kramer procedure or Tukey-Kramer multiple comparison procedure. This technique, as a follow-up, when and if you reject HO in a one-way ANOVA, this technique will then tell you where those differences are, whether mu1 is different than mu2, whether mu1 is different than mu3, whether mu1 is different than mu4, whether mu2 is different than mu3, whether mu2 is different than mu4, whether mu3 is different than mu4. It'll go through all those pairs and tell you which pairs are different. Okay, so that will be the follow-up, but we don't need to do it because we failed to reject HO. Okay, so I hope this was helpful. I'm going to do an example. This example quicker, cut to the chase with Google Sheets, so you can see how to do this with software. Okay, but the fundamentals were laid down here in these 4 parts. The calculations are going to be a lot easier because you're going to let Google Sheets do them for you. Okay, so I hope this series was helpful for you. This was all about one factor, one way ANOVA example by hand.